Welcome back, you guys. Today we are going to dive into the three states of matter. So, just to be clear, there is only three states of matter in this class that we will cover, and that is solids, liquids, and gases. On this picture, there are a couple of examples of solids, liquids, and gases. A couple of examples of solids are things like hats, pencils, tables, bicycles, computers, apples, a treehouse, and snow. Liquids can include things like things within a drink that you may drink, juice, water within a pool, hot chocolate, a bowl of soup, rain. Gases, a very good example of a gas is stuff like wind, helium for, let's say, a balloon, fog, and steam. So, just to recall, matter is anything that has mass and takes up space. So, no matter how big and how small you are, you all have mass and you all take up space. So, an ant, even though it's really tiny, does have mass and does take up space. You yourself have mass and take up space. Now, between the two, the ant has mass and takes up space, and you also have mass and take up space, but you seem to have more mass and seem to take up more space than an ant. So, in the example that I just gave you, an ant and a human does both have mass and take up space, but there is one that takes up more space than the other and may have more mass as well. So it doesn't matter what it is, the three states of matter are solids, liquid, and gases, and in each case, all of them have mass and take up space. Solids have mass and take up space. Liquids have mass and take up space. Gas have mass and take up space. So tracing back to our last unit, in our last unit, we talked about atoms. Atoms are what make up solids. Atoms are what make up liquids, and atoms are what make up gas. So it doesn't matter what we are talking about. Any specific thing that we may be talking about could either be a solid, liquid, or gas, but in either case, they get their mass from atoms. Atoms bundled together give mass, give weight to solids. Atoms give mass and weight to liquids, and atoms give mass and weight to gas. So, in summary, atoms make up the three states of matter. So, here's the real cool part, that depending on how much energy you add or remove, you can go from a solid to a liquid, or a liquid to a gas, or a gas back to a liquid, and then a liquid back to a solid. So it doesn't matter in what case you're talking about here, you can go back and forth between the different states of matter if you add or remove energy. Here's what I mean. Changes in states are the result of energy being added or removed. In this picture, the red represents hot or adding energy. The blue represents removing energy, or taking heat away. So here is a solid, and notice how the atoms in a solid are. They're tightly packed together. And if you add energy, they jump over to now becoming liquid. And now the atoms are slightly more spread apart. And if you continue to add energy to a liquid, it then becomes a gas. And in this case, the gas atoms are way more far apart than in liquid. However, if you remove energy and you take energy away, you can go from a gas back to a liquid. And if you continue to remove energy and you get it really, really cold, you can then become back into a solid. And the cycle can go back and forth. And this right here is all because you're taking energy away or you're adding energy into the system. So I would like for you to practice. Predict what happens to gas if energy/heat is removed. What would happen to these gas molecules and atoms if I remove energy and heat? You're right. If you remove energy, you can go directly into a liquid. However, if you remove even more energy, you can actually go into a solid. So, depending on how much energy you're removing, you can go from a gas to a liquid or from a liquid to a solid. So, let's dive directly into each state of matter, and we'll focus first on solids. So, solid, like this guy right here, he's a little ice cube. Solids have a definite shape and a definite volume. So molecules are tightly packed with a regular pattern and they vibrate in place. So what does this mean? This means like this ice cube has a definite shape. It has a shape where it's not really changing and it maintains its shape and maintains its volume. So if this guy is square, he's going to stay square. He's going to stay the volume of this square. And in here, all the atoms in this definite shape and volume are tightly packed. That means they're not really moving, but they are slightly vibrating. They're vibrating in place, but not moving so much. This is what I mean. Solids are, because they just stand still, they are very rigid. They have just one shape. So if I were to take this object and put it in a container, that specific solid object will maintain solid. It's not going to take the space of its container. Sorry, it's not going to take the shape of its container. It has a fixed shape and a fixed volume. So, solids have a definite shape and a definite volume, which means they don't change shape easily. They maintain their shape. So, if I put a orange within a bag, the orange is going to stay the size of an orange. It's not going to mold itself to the shape of a bag. It's going to maintain its shape and it's going to maintain its volume. These molecules in solids are tightly packed very, very close together, which gives them that um, uh, rigid type of pattern that maintains their shape. This also means that they can't be easily squashed. And they can't be squashed because they're already squashed. They're already squashed. They're as squashed as can be. They're not really moving much. They're just vibrating in place. Here's an example. Think of rocks or ice cubes. No matter where you place them, they hold their shape and take up the same amount of space. So think of a rock. Grab a rock and put it on a desk. It still maintains its shape. It's rigid, still maintains its shape and maintains its volume. Grab that exact same rock and put it in a soda can. It doesn't matter if it goes in the soda can or on the table. It still maintains its shape and it still maintains its volume. Now, let's dive into liquids. Liquids are slightly different though. Liquids have a definite volume, but no definite shape. Meaning that if I start off with 2 gallons of water, I'm gonna have that same 2 gallons of water. The only difference is that now they have a different shape. They have no definite shape. So if I put water within a water bottle, that water keeps its shape. Right now, this water droplet right here maintains its shape because it's probably in the mold of a water droplet. But if I were to get the liquid from here and then maybe put it on a table, the liquid will now take the shape of the table, which means that these molecules are loosely packed and they flow against each other. They can move more freely than they can with solids. This is what I mean. Liquids are not tightly packed like that uh, red square that you saw earlier. They are actually able to move more freely. So this guy can bounce over here. This guy can then bounce over there. He can bounce over here. He might bump into these other ones, but the idea is that he can more freely bounce around, which allows him not to be rigid. It allows liquids to also not have a fixed shape. They can mold the shape of their container and they have a fixed volume. They will take the volume of whatever container they're in. For example, here in this container, they're taking the volume of this container. So, in summary, liquids have a definite volume but no definite shape. Um, they take this shape of their container they are in because their molecules are less tightly packed than in solids. They're able to move around more freely, like I just showed you earlier. They're able to bounce around. They might bump into other ones, but they're able to bounce around very freely. But they cannot be squashed because they're already kind of squished. Not as much as solids though, but they are. If you squish them, they are going to not really move much. So they're not easily squashed as liquids are. Here's an example. A bottle of water has the same amount of water, whether you pour it on a cup or a bowl. The shape changes, but the amount of water stays the same. An ice cube, even though it's a solid, if an ice cube melts into a liquid and I grab that liquid um, on the table and then I grab that liquid with a towel, no matter where I get that liquid from, it's gonna maintain its volume. The only difference is that now it's taking the shape of the towel. Instead of taking the shape of the table where I left the ice cube at, it's now taking the shape of the towel. So, um, in summary, liquids are not rigid. They take whatever shape of whatever container they're in, and they have a fixed volume. So if I start off with 1 liter of water, no matter where it goes, it's still going to be 1 liter of water. And the final one is gases. Gases are very different from all these other ones. Look at this little guy. These gases crash out. They have no definite volume and no definite shape. So they're definitely not going to maintain their volume and they're definitely not going to maintain their shape. They are rascals. They go wherever they want. They take whatever volume they want. They take whatever shape they want. They don't listen to anybody. They don't like the rules. They break the rules often. So these molecules are very far apart and can move, which is why I said that they crash out. They go in whatever direction they want. This is what I mean. So this guy can move around, and it might take him a while for him to actually bump into another gas atom. This guy might move around. He might eventually bump into another gas atom, but it might be a while because as opposed to liquids and solids, these guys are so far apart, it's going to take them a while to actually bump into one another because they're just going in random directions. They are not rigid and no shape or volume because they are rascals and don't follow the rules. Gases have no definite shape or volume, which allows them to fill any container they occupy completely. So if I blow into a balloon, the air is going to fill up the space completely of the balloon. It's not going to stay in the beginning of the balloon. It's not going to stay towards the back of the balloon. It's going to not stay in the middle of the balloon. It's going to take the entire space of the balloon. These molecules are very far apart and they're moving very freely, which means they can be squashed if needed. Here's an example. Think of air inside a balloon. It fills up the entire space available, and if you let go, that air will spread everywhere. So, the air that was once in the balloon, I'm kind of limiting the air within the balloon to just the balloon. But the moment that I open that balloon up, it's going to go in all different directions. And instead of taking the shape of the balloon, now the air is going to want to take the shape of the classroom or whatever room you're in, whatever space you're in. So air does not follow the rules. They're not rigid. They have no fixed shape and no fixed volume, which means they can be squashed. However, I want to now focus on phase changes. So the reason why we talked about solids and having a fixed shape and volume, and the reason why we talked about liquids having a different shape and volume as well, and then how gases have a different shape and volume, is because you can go from a solid to a liquid or a liquid to a gas depending if you add or remove energy. So let's dive into that directly. Phase changes are when things go from a solid to a liquid or a liquid to a gas. In this picture on your doodle notes, you're going to notice that this picture right here represents solids because they're tightly packed together. This picture right here represents liquids because they're slightly more spread apart. And in this picture right here represents gases because they're very far apart. So this is what I mean. You can go in whatever direction depending if you add or remove energy. So I'm basically going to cover this because it shows us if there was energy removed or there was energy added, depending on what color this is. Like blue represents energy added. Blue represents energy removed. Red means energy added. So this picture is exactly the same as this. The only difference is that this doesn't color code it in blue and red for you, which is why I will cover this right here. Solids going directly into a liquid, that process right there requires you to remove energy and then slightly start heating it up. So start slowly adding energy to solids. That process right there is called melting. When you add energy to a solid, it becomes liquid. But if you continue to add energy, watch this. If you continue to add energy, you get a gas. And that process right there is called evaporation. If you add energy, though, like a lot of energy, like a lot of energy to a solid, it will become sublimation. It will be sublimated. Solids can go directly into a gas if they are sublimated and if you add a whole bunch of energy to it. Now, alternatively, you can go in the reverse direction. Like if this has a lot of energy as a gas and you slowly cool it down and it basically gets cold enough, you get something called deposition, where you go from a gas directly into a solid. But if you get a gas and you cool it, but not a lot, but just cool it just slightly, you get something called condensation, where you take something that's originally hot, like gas, and temperature wise though, something that's typically hot, and you really do a temperature change where you do cool it down, you get condensation and it becomes a liquid. And if that liquid right there, depending on what temperature it is, if you take that temperature of that liquid and you begin to freeze it, and you start getting it really cold, it becomes a solid. So you can go from a liquid to a solid, and that process right there is called freezing. So this is very similar to this. Solid to a liquid, that's called melting. Liquid to a gas, that part is called evaporation. Gas to a liquid is called condensation. Liquid to a solid is called freezing. And gas directly to a solid is called deposition. And finally, a solid directly to a gas is called sublimation. So this diagram is exactly the same as this one. The only difference is that I'm showing you this one because this one actually shows you a temperature change. So that being said, I would like for you to answer this question. What is the process of a liquid converting into a solid? What is the process of a liquid converting into a solid? That is called freezing. What is the process of a gas losing energy and turning into a liquid? That process of gas losing energy and turning into a liquid is called deposition. So gas starts off at one temperature, but it cools down and it loses energy. It becomes blue. That process is called deposition. What is the process of a gas losing energy and converting into a liquid? Gas. Losing energy and converting into a liquid. That process is called condensation. Gas, starting off at whatever temperature it's at, losing energy and getting blue and getting cold and becoming a liquid is called condensation. One more example. What is the process of a solid gaining energy and turning into a gas? Solid gaining energy. So that means it's originally one temperature and you start adding energy to it. You start adding heat to it. What does it become? Start adding heat to a solid. It becomes sublimation. Solid adding heat to it and turning into a gas is sublimation. And last but not least, what is the name of the phase change where a liquid gains energy and turns into a gas? So a liquid directly into a gas, what process is that called? Good, evaporation. Evaporation is when a liquid starts off at whatever temperature it's at and it gains energy, it becomes red, and it eventually becomes a gas. That process is called evaporation. And that right there completes our states of matter recording. Good job, you guys.